Welcome to this explainer. Today, we are taking a completely different, highly strategic approach to the Cambridge Physics syllabus. Whether you are studying syllabus code 0625, 0651, 0652, 5054, or 9702, we are treating your next exam exactly like a high-stakes legal brief. Think about it for a second. A top-tier barrister doesn't just walk into a courtroom, throw a bunch of isolated random facts at a judge, and simply hope they stick. Absolutely not. They build a bulletproof case. They present hard evidence. They provide clear sequential reasoning, and they drive it all toward an undeniable conclusion. Today, we are adopting that exact same ruthless precision mindset for mastering the core mechanics of forces, pivots, and turning effects. I want you to imagine two classic students right now. First, we have Alex. Alex works incredibly hard, but completely overloads every single exam answer with raw physics facts, dumping formulas onto the page with zero actual analysis. Then we have Sam. Sam knows the material, but always rushes, completely missing the command word requirements and leaving easy marks on the table. Both Alex and Sam walk out of the exam hall feeling confident, and both end up devastated on results day. By the end of this explainer, you are going to learn exactly how to avoid their mistakes. You won't just be blindly memorizing formulas anymore. You will be constructing airtight, flawlessly structured arguments that examiners literally cannot help but award full marks to.
Okay, let's dive right into the deep end by starting with a massive challenge question straight from a real Cambridge past paper mentality. What physical effect, measurement, or prediction depends entirely on understanding forces and turning effects? I want you to really think about that. We are starting here because it makes the concept feel absolutely vital and necessary, rather than just some decorative, abstract physics trivia you have to memorize for a test. If you can't answer this question confidently just yet, don't worry at all. This right here is the foundation of our entire case. We absolutely need to understand exactly why this specific physics matters before we start writing down a single equation. When you anchor your learning in reality, when you truly realize that everything from opening a heavy door to balancing a massive suspension bridge to simply unscrewing a tight bolt on a car tire relies heavily on these exact principles, you become significantly less dependent on memorized textbook wording. Instead, you become much more capable of reasoning your way through those tricky, unfamiliar exam questions that Cambridge loves to throw at you. Remember our student Sam who always rushes? Sam looks at a question about a crane and panics because it wasn't the exact seesaw example from the textbook. But when you build your case on the underlying physical effect, the specific object in the question simply doesn't matter anymore. You know the law, and you know how to apply it.
To avoid the trap of just memorizing isolated facts, which is exactly what causes our other student Alex to lose so many marks, we are going to use a concept-first approach. This strategy is all about moving gradually, logically, from everyday language, the way you and I naturally speak to each other, into strict, highly precise physics vocabulary. Think of it kind of like translating your raw common sense into admissible scientific evidence. You already know intuitively that you need to push a heavy door far away from its hinge to open it easily. You wouldn't try to push a door open by pressing right on the metal hinge, right? That's your everyday language. But by starting with the concept first, we build a logical chain. We anchor your understanding in that physical reality before we ever introduce the formal math, the center of mass calculations, or the complex symbols. This is exactly how you build true scientific intuition. And let me tell you, in a high-pressure Cambridge physics exam, intuition is your absolute best defense. It's the lie detector that tells you if your final calculated answer actually makes sense in the real world.
Now, to meticulously build our case, we use a core four-step blueprint. Step 1, identify the quantity or phenomenon you're looking at. Step 2, state the exact mathematical or physical relationship involved. Step 3, explain the underlying physics clearly. And Step 4, connect it to a real-world observation, an experiment, or a specific device. Now, if you are a savvy student, you might recognize that this perfectly mirrors the legendary Peel framework. Point, evidence, explanation, and link. Identifying the phenomenon is your point. Stating the relationship or formula is your evidence. Unpacking the underlying physics is your explanation, and connecting it to a device is your link back to the question. This sequence is absolutely critical in these exams because examiners are actively hunting for a very specific combination. They want to see both deep theoretical understanding and practical application. Before we continue unpacking this framework, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, whether you're calculating the moment of a force or describing a complex system sitting perfectly in equilibrium, applying this exact four-step Peel structure guarantees your answers deliver exactly what the mark scheme demands.
Notice how we strategically build our argument by starting with concrete, everyday examples on the left side of our mental ledger. Only when that foundational groundwork is firmly laid down do we introduce the heavy symbolic relationships on the right. Instead of jumping straight to the rigid formula for a moment, we start with the physical, undeniable reality of two kids sitting on a playground seesaw. We establish why the heavier child absolutely needs to sit closer to the middle pivot point to balance it out. We stress what that turning effect actually feels like physically before we ever write down m equals F times d. You bring the everyday reality to the physics terminology, not the other way around. This is where Sam fundamentally goes wrong. Sam looks at the exam paper, sees the word equilibrium, and immediately starts frantically writing down symbols without visualizing the physical system. But if you pause, visualize the seesaw, establish your everyday language, and then translate it into physics vocabulary, your argument becomes unbreakable. You are essentially proving to the examiner that you haven't just memorized a string of letters, but that you actually comprehend the mechanics of the universe.
So, the absolutely crucial point here, and this is a direct quote you need to burn into your memory, is to insist on cause and effect rather than isolated facts. Whether you are dealing with gravitational fields, subatomic particles, or in our case turning effects, Cambridge examiners heavily reward a crystal clear chain of cause and effect. In our specific case today, the cause is a force applied at a specific perpendicular distance from a pivot. The effect is the resulting turning motion, which we call the moment. If you just list facts like our student Alex does, you are literally just handing the examiner a box of random puzzle pieces and expecting them to do the work of putting it together. Examiners will not do that. They will just deduct marks. But if you clearly explain the cause and effect, you are putting the puzzle together for them. You are leading the judge right to the verdict. You are making an undeniable argument that commands top marks.
Let's move to where this actually matters in the real world, because this is where the link in your Peel framework really shines. We're talking engineering, safety, transport, energy systems, communications, medical technology, and even astronomy. Top students, the ones securing those highest grade boundaries, can always name at least one real, tangible situation from this list where predicting outcomes relies completely on turning physics. For instance, how a civil engineer meticulously calculates the precise pivot point and counterweights of a massive construction crane to prevent it from tipping over and causing a catastrophe. If an exam question asks you to apply a turning effect, you should instantly be able to pull from fields like these. It proves to the examiner that your knowledge isn't confined to a sterile classroom textbook, but is actively solving real-world safety and engineering problems. When you can connect the formula on your page to a wind turbine generating energy or the precise mechanics of a medical prosthetic limb, your exam paper instantly stands out from the thousands of others the examiner has to read that day.
Now, here is where things get serious. This is where so many students fail to make their case to the examiner and fall directly into the dreaded exam trap. Have you ever walked out of an exam hall feeling incredibly confident because you successfully remembered and wrote down the right formula, only to get your graded paper back weeks later and see you lost half the marks on that question? It is literally one of the most frustrating things a student can ever experience. But let me tell you, it happens all the time. Why? Because knowing the formula is only step one. It's like having a murder weapon in a trial, but completely forgetting to explain to the jury how it actually connects to the suspect. The formula is just a tool. Your explanation, your reasoning, and your applied argument are what actually earn the points. If you just write down force times distance and move on, you are falling right into the trap.
Let's look closely at exactly why that happens. These are the examiner-verified most common weaknesses, and I guarantee you've made at least one of these mistakes. First, writing the correct formula without explaining the variables. If you write m equals F times d, but you fail to specify that d absolutely must be the perpendicular distance from the pivot to the line of action of the force, you lose the mark. Period. Second, quoting a process without linking it to a physical effect. And third, dropping a real-world example into your answer, but completely failing to show why it follows from the physics. Let's do a quick mental find the flaw challenge. Imagine Alex writes, to balance a ruler, put a weight on the other side. This is the principle of moments. What's the flaw? Alex completely missed the explanation. There is no mention of clockwise moments equaling anti-clockwise moments. These errors perfectly show what happens when you try to take a shortcut. The examiner cannot and will not give you marks for what they assume you know in your head. They can only legally grade what you've proven explicitly on the page. To counter those exact errors, you must structure your answer like an undeniable legal argument, using this, the safest exam method on the planet. First, give the definition. Second, state the relationship. This is where your formula or rule acts as your hard evidence. Third, provide the explanation, establishing that clear cause and effect chain. And fourth, application, connecting it to a real-world use or an experiment. Stop scrolling.
Subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, getting back to our method. For turning effects, you define the moment. Relate it mathematically as force times perpendicular distance. Explain exactly how increasing that distance amplifies the turning force. And finally, apply it to explain a lever like a spanner. If you follow this rigorous structure, you leave absolutely zero room for the examiner to doubt your understanding. You win the case every single time.
Let's see this transformation in action. I want you to imagine a 60-second speed writing challenge. On the left, we have a notoriously weak answer. It just scribbles down moment equals force times distance, and maybe throws in a poorly memorized half-correct sentence. It might technically contain a sliver of true information, but it bleeds marks for rote memorization without any context. Now look at the strong answer on the right. It acts like a true strategist. It formally defines the moment as the turning effect of a force. It explicitly explains that increasing the perpendicular distance from the pivot proportionally increases that turning effect. And then, crucially, it applies that rigorous reasoning to explain why it is vastly easier to loosen a rusted, tight nut with a long-handled wrench rather than a short one. The strong answer is a beautifully argued legal brief that commands respect. The weak answer is just a messy pile of scribbled notes that the examiner is going to dismiss immediately. Which one do you want your exam paper to look like?
Whenever you sit down to face a Cambridge 0625 or any other structured physics paper, expect to tackle these exact tasks. This is all about command word decoding. When the command word says define, you state the key idea and the rule, like the principle of moments. When it says explain, you must use a cause and effect chain. When it says describe, you detail an experiment or calculation, perhaps outlining the exact steps to find the center of mass of an irregular piece of card using a plumb line. And when it says state and justify, you give a real-life example and defend the physical link. If you've been following our 4-step Peel blueprint, you don't even have to panic when you read these command words. You are already perfectly mathematically calibrated to answer every single one of these prompts. You are simply delivering what the court, the examiner, has explicitly asked for without wasting time on irrelevant details like our friend Alex often does.
To lock this entire strategy down, I want you to use this quick recall matrix. This is your ultimate time management and data scan tool. I want you to test your absolute mastery of forces and turning effects with these 4 prompts before you ever step foot near the exam hall. Prompt 1. What is the core idea? Prompt 2. What changes physically in the system? Prompt 3. What specific quantity, formula, or graph proves it? And prompt 4. Where is it used in the real world? This table acts as your personal, ruthless diagnostic tool. If you look at this matrix regarding turning effects and your mind goes blank on column 3, you know exactly where your case is weak. You know exactly what you need to review tonight. It is how you systematically ensure there are 0 holes in your testimony before the cross-examination of the final exam begins. You should be able to scan any physics topic and run it through this exact matrix in under 60 seconds.
Take this advice from the source material to heart. It says, if you can answer those 4 prompts aloud, the topic is usually secure enough for short answer and structured questions. Notice the absolutely critical word there, aloud. Speaking your answers out loud is the ultimate, undeniable test of whether your physical reasoning is truly secure. It forces your brain to articulate the cause and effect clearly, rather than relying on that vague, fuzzy, yeah, I kind of get it feeling we sometimes let ourselves get away with when just reading silently. If you can explain the principle of moments out loud to an empty room, smoothly and without hesitating or stumbling over your words, your case is rock solid. You have transformed from someone who just hopes to pass into a confident strategist who dictates exactly how many marks they are going to take home.
Before we wrap up this explainer and finalize your system, I'm going to leave you with a final, practical challenge to test if you can truly build an undeniable physics case entirely on your own. I want you to literally look around the room you are in right now. What everyday object, maybe it's the door handle, a pair of scissors on your desk, or even the hinge of the laptop you're looking at, relies entirely on forces and turning effects to function? Identify it, state the mathematical relationship, clearly explain the physics, and apply it. Ultimately, the entire physical world around you is constantly balancing on pivots and turning effects. The only question is, are you ready to prove it to the examiner? Students who implement these exact physics strategies see an average improvement of 2 full grade boundaries. But that only happens if they practice consistently with our weekly content. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams,
at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Finally, drop a comment below with your target grade for physics and the biggest challenge you're currently facing. Our team responds to every single comment. Like and share this with a study partner. Ace the exams. Your Cambridge success starts here.